Hello everybody, thank you for joining for my presentation today. My name is Nathan Daubenmeier. I'm from the Ohio State University, and today I will be presenting on high throughput CALPHAD-Based thermodynamic and kinetic evaluation of stainless steel solidification. As I said, I'm from the Ohio State University. I recently graduated with my bachelor's in mechanical engineering, and I am now pursuing a master's and a PhD in welding engineering at the Ohio State University. I'm projected to graduate in 2025. I am also working as a material scientist for brazed alloys at Morgan Advanced Materials, and I'd like to say a special thanks to them as they support me through grad school. I would also like to acknowledge Antonio Ramirez, my advisor, as well as Benjamin Sutton, who did a lot of the work that will be presented today, and I was working in conjunction with him for several years before he graduated with his PhD. This research was funded by the Department of Energy, and the grant number is listed there. My contact information is also listed. If you'd like to reach out to me with any questions, feel free to do so. The motivation for the research that is going to be presented today has to do with the solidification cracking propensity for stainless steels. As we know, primary austenitic solidification tends to be more susceptible to solidification cracking than ferritic solidification does. Primary ferritic solidification, particularly FA mode solidification, reduces solidification cracking risk for a couple of factors, one of which is the more tortuous grain boundaries that are present in ferritic FA mode solidification. This tortuous grain boundaries makes crack propagation harder, and it takes more energy for the cracks to propagate. Ferrite to ferrite and ferrite to austenite boundaries are also less easily wet by liquid, which helps prevent solidification cracking. And the higher solubility of impurity elements that ferritic grains have, as opposed to austenitic grains, helps to avoid solute collection at grain boundaries, which can also contribute to solidification cracking. So these factors help reduce risk of solidification cracking in primary ferritic steels, and so it is important to know how our steels are solidifying, what the primary solidification mode is, so that we can make sure that we are avoiding solidification cracking. For this reason, several people have created constitution diagrams over the years, which help allow us to predict the solidification mode based off of composition alone. The Schaeffler diagram was one of the first widely used diagrams that was published. It was published in 1949 and explores a broad compositional range, but has some limited accuracy for austenitic stainless steels and stainless steels in general. In particular, duplex stainless steels can be a little hard to use the Schaeffler diagram for because it's missing a couple important elements from the nickel and chrome equivalencies, which have a pretty big factor. One of those is nitrogen is a very significant austenite promoter, and it has a large coefficient on most diagrams, and it's not present in the Schaeffler diagram, which means that there's just limited accuracy there. For that reason, the WRC 1992 diagram was produced, which is and has been for several years a definitive diagram for austenitic and ferritic stainless steels. For this diagram, they used 152 alloys for solidification mode regression and 923 alloys for the ferrite number regression. That's a lot of experimental alloys that they used that provided the data that they could do regression on in order to get the diagram that is shown and that we have all likely seen and used. So this diagram is really great and has done a lot of been very important for the research in the year since it was published. But with advances of computational modeling, we began to wonder if we could model this diagram and if it would match up, or if there was going to be a discrepancy that would need to be investigated. For that reason, we took the original 193 alloys that the WRC diagram used in order to create the primary solidification mode lines. That's shown on the figure on the left. Those are the original data points and the original characterization of those welds that they did in order to create the regression lines that are shown. Then the figure on the right shows the same data points, but we simulated them in thermodynamic software and were able to test the primary solidification mode. As you can see, there is a shift between the WRC diagram and the thermodynamic software, and where they predict the shift between primary austenite and primary ferrite solidification. So this indicated that there is room for further exploration, and so that is what we did. In order to continue exploring this, we took the published concentration ranges for each element that is listed in the WRC diagram, which are kind of the general composition ranges of stainless steels, and we used those concentration limits to generate 11,000 randomly generated steel chemistries, which aren't necessarily real chemistries, but are all have composition ranges that fall within standard limits, and places them all on the WRC diagram with the WRC equivalency equations. So we used this theoretical steel database in order to simulate a lot of different alloys across the WRC space, which would allow us to do statistical analysis. This figure here shows all of those points. All of those alloys were plotted using the WRC equivalencies on this figure, and then the WRC line that separates primary austenite and primary ferrite solidification is also shown on the graph. The blue dots represent primary austenite prediction from the software, and the red dots demonstrate primary ferritic solidification as predicted by the software. So as you can see, there's a shift between the WRC line and the what's being predicted by the software, and the figures on the right show a little more clearly that separation between the two. So seeing this shift, we decided to proceed with creating our own equivalencies in order to better understand the impact of the elements in the thermodynamic software and see how that relates to reality. In order to do this, we used the Scheil equations, and Scheil solidification equations use an iterative process to simulate solidification from fully liquid to fully solid, and it uses a couple assumptions, including there's no solute diffusion in the solid state, and there's no undercooling. There's also infinitely fast diffusion within the liquid phase, and a couple other assumptions that are used. But this is generally a pretty good model for solidification of weld metals. And using this, we defined a delta fraction solid parameter in order to help us describe whether the primary solidification was primary ferrite or primary austenite. So the figure on the right shows how we did this. So in the top left, we have a primary austenite and fully austenitic weld, which results in a delta fraction solid of 1, meaning that it is fully solid before any other phase is formed. The bottom left shows a sample that is primary austenite, but produces some ferrite partway through solidification, resulting in a delta fraction solid of 0.6. The figure in the bottom right shows a alloy that is primary ferrite and produces some austenite partway through solidification, resulting in a delta fraction solid of negative 0.6. And then the figure in the top right shows an alloy that is purely ferritic, and so it results in a delta fraction solid of negative 1. What this delta fraction solid parameter does is it allows us to do statistical regression between the composition of the alloy and the delta fraction solid parameter in order to allow us to relate the elements and their influence on solidification, primary solidification mode. Doing this regression on the 11,000 random data points that we created, we were able to come up with a couple equivalency equations. The first one we used backwards elimination, multiple linear regression, in order to create the equivalency equations. This is a pretty conventional regression method similar to what was done in the WRC diagram, and that produced the equations that you can see in the top right. They are somewhat similar to what the WRC diagram shows, with slightly lower values for the carbon and for the nitrogen, which help in the nickel equivalency, which helps to reduce that discrepancy that we saw between the simulated and the WRC diagram. And this did a better job of differentiating the theoretical data from what the WRC diagram was doing, but we also noticed that there was a bias in certain elements that indicated a nonlinear correlation between some of those elements and the primary solidification mode. So in order to address this, we allowed the regression model to use a chrome power and a nickel power with independent terms from the linear chrome and nickel equivalencies. And we did the regression again, and we got the equations that were shown in the bottom right. So these are a slightly less conventional method for what most constitution diagrams do. Using powers for certain elements is typically not done, but that doesn't mean that it shouldn't be done. I think that there's not really anything that says that the correlation between the elements that you put into your weld metal and the primary solidification mode has to be linear. So doing this regression resulted in what we see on this slide. So here you can see, again, similar graphs to what we've seen before. Primary austenite is colored in blue, primary ferrite is colored in red, and the figure on the left shows the standard linear regression that we did, which is, again, the more conventional type of regression. And it did a pretty good job of differentiating between primary austenite and primary ferrite, although there is still a little bit of overlap between the two. If you're close enough to the screen, you may be able to see that. But a better job than what was done by the WRC equivalencies. And then on the right, we have the nonlinear regression that was done, which does a really good job differentiating between the primary austenite and primary ferrite as predicted by the thermodynamic software. Using this, we created this diagram, which is our diagram for the primary solidification mode. So if you're in the top left region, that's labeled A, you're guaranteed to be primary austenite. If you're in the bottom right, you're guaranteed to be primary ferrite using standard solidification or standard welding procedures. The region in the middle, though, is an area where we notice a lot of discrepancies, where you were not always guaranteed to have either primary austenite or primary ferrite. And one of the reasons for this is because of the kinetic dependence of solidification, and it's not purely a compositional phenomena. So because of that, we did some modeling and calibrated for the metastable primary austenite growth in order to help allow us to kind of capture the range where there's some uncertainty about whether austenite will form or whether ferrite will form. And so that's what that little channel in the middle is. After doing this, we have a good diagram that we could use based off of the experimental data or the theoretical data, but we wanted experimental validation. For that, we took several different stainless steel wires and created dilutions of them, and then made small buttons. Each of these buttons was melted using gas tungsten arc welding, and then they were cross-sectioned and characterized under a microscope in order to determine the primary solidification mode. So the figure on the left shows all the same data points plotted on the WRC equivalencies, and the figure on the right shows the same data points plotted on our new nonlinear regression equivalencies. Some interesting things to note on the WRC diagram or WRC equivalencies. There are several compositions which were predicted to be primary ferrite from the primary solidification mode line. They're below it, but solidified as primary austenite. And so these are some of the concerning points for us, where you may have a weld that you think would be safe because it is predicted to be primary ferrite, but it ends up solidifying as primary austenite and could potentially have solidification cracking problems. The figure on the right shows a more conservative line. The solid black line is a more conservative line, where if you are on or below that line, you're guaranteed to have primary ferrite, and if you're above that line, you may have mixed mode, you may have primary austenite, you may have primary ferrite, and then by the time you get to the dotted line, you're guaranteed to have primary austenite above that line. So from this, it was really interesting to see that the theoretical simulations did have significant improvement over the WRC diagram, and shows that with the ability to simulate a lot more data points than what you could physically test, and allows us to capture some of the behavior of these elements a little bit better. So this is the end of the presentation. I think that one of the big takeaways from this is that computational modeling allows us to do a lot of interesting things with alloy design that hasn't been around for the last couple hundred years. And so I'm a big advocate for what we can do with modeling, and it's not the end all be all. We need to have a lot of experimental validation for the models that we're producing, but I think it's a really powerful tool where we can simulate hundreds and thousands of points and model things that we haven't been able to see before. So I'd like to urge you to continue to consider modeling and how it may help your research projects. Finally, here are my references. Special shout out to Benjamin Sutton for all the work that he did on this project. And that is the end of my presentation. Are there any questions?